Hi, I'm Chris.
I'm Alec.
I'm Jake. I'm Jason, and for our EECS-373 project, we created a low-powered energy harvesting soil monitoring system. Our soil monitoring system, dubbed the Green Thumb, is a solution that was created to address the problem of gardeners and farmers having to constantly monitor the moisture levels of their soil. What makes our solution so unique is that it's low-powered and transmits its data wirelessly. Because it's an energy harvesting system, all it needs as a power source is a solar cell. Whenever the solar cells collect enough energy, the Green Thumb will wake up, take soil moisture and temperature readings, and then send the data wirelessly to a base station for analysis. This would make monitoring soil conditions much easier and more convenient for taking care of large plots of land. There are other soil moisture sensors out there on the market, but they require larger power sources and certainly don't transmit data wirelessly for their users, so they would need to make rounds around their land to monitor the soil conditions on each plot. What makes our solution so ideal is that the only thing users would need to do is place it in the soil and let it take measurements on its own. Users can then check their soil conditions remotely from an application that runs on their computer using a wireless receiver. The Green Thumb uses capacitive sensing to determine the moisture of the soil. As the soil's moisture content changes, the capacitance of the soil changes. This capacitance can be detected by repeatedly charging and discharging the soil while monitoring rise times. Shown here, wetter soil responds much faster to the input square wave than drier soil. The Green Thumb takes 100 samples of these using digital I/O to measure the soil capacitance. For reading temperature, the Green Thumb uses a thermocouple read by an ADC via an interrupt-based method. These measurements are then transmitted over a Bluetooth Low Energy advertisement packet to be read by a receiver. Our client software then reads these measured values and plots them in real time. All of this measurement is done using a mere 5 millijoules of energy, provided by our custom solar energy harvesting circuit board. When enough energy charges the capacitors on the board, it will discharge the stored energy into the soil sensor, powering the device long enough for it to do its job in under half a second. Enough solar energy is harvested in around 5 seconds on a partly cloudy afternoon in Ann Arbor. This demonstration shows how little energy it discharges, only enough to make an LED blink for a moment. As you can see, we had to seriously optimize our measurement and data transmission process in order to get our sensor to work properly. In order to actually measure the capacitance of the soil, the sensor uses 2 spaced probes. One probe acts as an output and sends a pulse by setting a digital I/O pin high. The microprocessor, which in this case is the Nordic Semiconductor NRF51822, captures this time through the use of a timer in the microcontroller. The soil then acts as the RC component of an RC circuit, and the pin's output acts as a step input. As such, we can measure the step response of the soil to determine the time constant of the circuit. When the second I/O pin triggers high, which is at 70% VCC, the sensor captures that time. This time is longer when measuring dry soil and shorter when measuring wet soil, directly related to the capacitance of the soil. This time delay is the information that is sent to the receiver for processing. With our proof of concept, we are able to provide reliable, consistent measurements in packed soil with low clay content. We can also successfully measure and send data within the window of time provided by our solar energy harvester. However, our sensor needs further calibration to work properly in other types of soil. Moreover, our sensor must be in sunlight to make any measurements, so the frequency at which measurements are made is dependent on the availability of light. Also, the transmission range of our device is only 10 meters and cannot transmit through walls, which would be a challenge for users who want to monitor crops remotely. We would like to continue with this project and work on these drawbacks, mainly to increase the range of our data transmission and the accuracy of our sensor. Given our current means of production, these sensors can be produced at a cheap price at about $20, and with further improvements in range and calibration, I can guarantee that we will have a competitive, effective product for gardeners and farmers alike. Thanks for watching.